Hi, I'm Ty, and I'm here to tell you more about a poster that I presented at CDS 2026. The Cognitive Development Society's International Conference, CDS 2026, was held in Montreal, Quebec. Topics focused on growth and change in intellectual processes like thinking or reasoning. I presented a poster at the conference showcasing the work of our team at the AIM Research Center at Carleton University. Let's dive in. The project is titled Finding Theory in the Classroom, Validating a Teacher-Led Numeracy Screener Using Classical Effects from Numerical Cognition. In numerical cognition, there's a variety of classical effects, which explain how people learn and process numerical information. Now, these effects are mostly found by trained researchers and in controlled lab settings. Real life is a bit messier. So we had real teachers use our digital screener in real classrooms to see how their students are succeeding or struggling in math. Now, there have been some studies which have looked at classical effects in classroom settings. However, we are looking at 5 effects at the same time and at a very large scale. For each effect we looked for, we had at least 450 students in each grade, with a total sample size of around 5,000 students. And good news, the same patterns emerge in the lab and the classroom. This leaves us with 2 conclusions. First, this is evidence of ecological validity. Classical effects in numerical cognition can be generalized to real life. And second, this is also evidence of construct validity. The screener we developed and are using accurately measures what we want it to. The Early Math Assessment at School, or EMA, is based on over 30 years of research on early math learning. It is a paper and pencil formative assessment used to help teachers identify and address gaps in early numeracy skills. We partnered with Vreda, a Canadian company that specializes in digital assessment, to develop a digital version of the EMA called the DIMA. It has already been piloted with over 20,000 students across Canada. Now let's look at classical effects. There are greater error rates on close distance trials, for example, 1 versus 2, compared to far distance trials, for example, 1 versus 6. We used a number comparison task to investigate canonical distance effects. Students are presented with 2 numbers and asked to click on the larger number. Looking at the figure, we can see that error rates go down as the distance between the numbers increases. Additionally, students improve in older grades. There are lower error rates for adjacent ordered sequences like 1, 2, 3 than for non-adjacent ordered sequences like 1, 4, 5. We used an ordering numbers task to investigate reverse distance effects. Students are presented with 3 numbers and asked whether they are in an increasing order. Looking at the figure, we can see that the ordered sequences, orange lines, have lower error rates when sequences are adjacent than non-adjacent. Additionally, this pattern continues in grade 3, and their performance is better than grade 2. There are more errors on problems with larger operands, like 6 plus 7, than smaller operands, like 1 plus 2. We used addition problems to investigate problem size effects. Students are presented with 2 numbers, operands, and asked to add them. Looking at the graph, we can see that the pattern continues across grades 1 to 3, with students getting progressively better. Ties are problems that add the same numbers, for example, 5 plus 5 or 2 plus 2. There is a smaller percent absolute error for numbers that are closer to the midpoint of a number line. And so, we used a number line task to investigate a midpoint advantage. In a number line task, students are asked to place numbers like 420 on a line from 0 to 1000. Students from grades 4 to 8 were asked to place numbers 97, 420, and 982 on a line. Students in grade 3 were also asked to place numbers 211 and 580. There were not enough trials to see a complete tri-anchor pattern, but we can still see the distinct advantage in placing numbers closer to the midline. With more trials, we would expect a tri-anchor pattern to emerge. Natural number bias errors are due to treating fractions like natural numbers. For example, thinking 7/18 is larger than 6/9 because 7 is bigger than 6 and 18 is bigger than 9. We used a fraction task to investigate natural number bias. For example, students were asked which fraction is greater than 6/9 and given 4 options to choose from. Looking at the graph, we can see that students from grades 4 to 8 have more errors that would be expected due to chance, and students do better in later grades. Now, this wasn't shown in the poster, but as you can see in this figure, even grade 8 students have more natural number bias errors than other errors. Our results show classical numerical cognition effects from theory also emerge in the classroom and support the validity of our numeracy screener. Moving forward, we can now do more detailed analyses with data obtained from our digital numeracy screener.
Hooray! For more information, visit these links.